Okay, so my talk is on the Liskov Substitution principle. And so I saw this on a poster. If it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. So it's a good way of thinking about Liskov. So what is Liskov substitution? Normally it's that Russian one you can't ever remember when you're asked in an interview. That's the one, like, whenever I'd be asked, I could always get all the other ones, and it's like, yeah, that Russian one, I don't know. But even then, I never really knew what it was. And so this is one that I think a lot of people struggle with, because you'll watch a YouTube video, you'll read a blog post, and after it, you basically like, okay, well, I read the words, but I think I feel dumber now. So first of all, let's talk a little bit of history. So Liskov substitution is named after Barbara Liskov. And so one of the things that I discovered while doing this was how awesome Barbara Liskov is. I never really, I always knew, like, it's named after her, but I didn't really ever know anything about her. So she's an institute professor at MIT, as well as a Ford professor in its School of Engineering and Electrical Engineering. She's one of the first women to be given a doctorate in computer science in the U.S. She's a Turing Award winner and a John von Neumann Medal winner for her contributions to program languages, program methodologies, and distributed systems. So I think we can all agree she is very qualified to have her own principal. I hope that I can do half of what she's done. So really interesting, and I highly recommend you read more about her. So let's talk about the principle itself. If S is a subtype of T, then objects of type T in a program may be replaced with objects of type S without altering any of the desirable properties of that program. So that is Liskov substitution. I'm going to turn it over to Brandon for interface segregation. No, I'm just kidding. So let's see if we can make that a little bit simpler terms. At its core, the Liskov substitution principle states that subtypes must be substitutable for their base types. So, first let's kind of talk about a couple of the terms that we're using. So, how many people are familiar with the concept of inheritance? Okay? So the idea behind inheritance is we will define either an interface or a base type, and then we'll say that another object will extend that, or sometimes you'll say an object is a type of object. So what we want to do, and kind of really at its core, and hopefully by the end of this we'll all understand it, is if I have, going back to our employee example, a object of type manager, and it inherits from employee, then we should be able to use either of those classes and not affect the behavior of any calling applications. So when you have a calling application, they are going to make certain, they're going to have certain expectations. They're going to believe that your code is going to work a certain way. And so as part of that, we need to ensure that those hold true. So a big part of this is the concept of substitutability. As part of that, child classes must not remove base class behavior and not violate base class invariants. Who here knows what an invariant is? So an invariant is essentially something that we believe is not going to change. So the calling application is going to assume that certain things are going to remain the same. So if we go in and we violate those base class invariants, I keep cutting out. Try that. If we go and violate those invariants, then we are going to create defects in our calling applications. And our customers don't like defects. Not sure why, but they complain a lot when we give them to them. So it's best not to do it. So this is where we get into the idea of inheritance and the ISA relationship. So in naive object-oriented programming, we will oftentimes use the term ISA to describe child classes and their relationship to base class. So you might say a manager is a employee. The problem is with Liskov is you should not say is a, but it should be replaceable for is substitutable for. So if you think about the classic example of Liskov substitution, which we are going to look at because I'm legally and contractually obligated to show it, is the idea of a square is a rectangle. So in geometry, we know that a square is a type of rectangle. However, a square has certain properties and characteristics that are unique to it. So we then ask, is a square substitutable for a rectangle? That's where we start running into problems. So to kind of help me understand this a little bit more, I decided to take a more abstract thought. So let's take a Hollywood actor. So we can say that we have a base type of Hollywood actor, and that of that, we have Tom Hanks. So Tom Hanks is an actor. There are certain properties and things that means. So it means that he does act, that he might have a collection of awards. And so, you know, Tom Hanks has made many great movies, and he is a very much beloved actor, award-winning, and all-around national treasure. Now, we could take another actor, say Nicolas Cage. Now, Nicolas Cage is by definition an actor, but can we substitute Nicolas Cage for a Tom Hanks? I would argue we can't. Just because he fulfills the contract of an actor doesn't necessarily mean that he can step into that role. Even though he may have won some awards, and he did star in a movie called National Treasure. I would not necessarily consider him a national treasure. And I'm pretty sure that we, as a consumer of that actor, would say that we had invariance violated if we went to see a movie expecting a Tom Hanks, but instead got a Nicolas Cage. I go to see Apollo 13. It's an inspirational story of human struggle. But then if you substitute Nicolas Cage, all of a sudden you're rooting for the exploding oxygen tanks. So while he may have been able to fulfill the contract, he is not a good substitute. Hashtag Nicolas Cage is a Liskov violation. So, and my goal is, you know, go and tweet that. I want his publicist to have to make an official statement saying that he is not a Liskov violation. So with that, let's take a look at some code. Take a second for it to sync up. So let's see. So one thing you'll notice, I'm using a Mac, so I'm doing my demo with Visual Studio Code using .NET Core. So one of the really cool things is with .NET Core, it's cross-platform. We can use Windows, Mac, Linux. So I definitely wanted to show that. Also, if you've never tried Visual Studio Code, I could not recommend it more. It is my favorite code editor by far. They're constantly making enhancements to it, and it is just awesome. So first, we're going to take a look at a project called Shape Tests. And so this is the one that I am legally and contractually obligated to show. So I am hopefully meeting all of the legal requirements. So first, we're going to take a look at some unit tests. So if we look here, we have a unit test, and it is asserting that we get back an area of 6 for a 2x3 rectangle. So this code is going to do an area calculation given a rectangle. So let's just run this test and see, does that hold true? So we've built, we're showing total test 1, passed 1. So given a rectangle of a height of 2, width of 3, we did indeed get an area of 6. So now let's look at another one. So this is for a, we should get an area of 9 for a 3x3 square. So we have created a new square. Because by definition, a square has equal sides, we are only passing in a height. And in a minute, we'll take a look at the square class and see why that's important. So if we run this test, we should see it pass, and it does. So we have a total of 1 test, 1 passed. So now let's get a little bit crazier. We're going to see that we get an area of 20 for a 4 by 5 rectangle from a square. So we're going to create a new rectangle and set it to new square. Because they both inherit from shape, this shouldn't be a problem. We're going to set the rectangle's height and width just like we would expect. Let's run it. And it failed. So at this point, we have found a Liskov substitution violation. We assumed that even though square inherits from rectangle, that we should be able to then swap them, but we are not able to. So if we run a debug, we'll be able to see the error. Take it a second to load. In just a moment, I promise it will break. Take back every nice thing I said about Visual Studio Code. So we'll give that another second.
Can you have InCrunch as well here?
No, InCrunch won't work with VS Code at this time. Well, it is not doing what I expect, but...
We'll fix it next month.
Exactly, there we go. So let's take a look at the code, and maybe we can figure out what's going on here. So for our area calculator class, we have 2 static ints of calculate area. One takes in a rectangle and one takes in a square. So when we did our call with the rectangle, we are returning r.height times r.width. And that returned what we expected. So when we did this, 2 times 3 is 6, and that worked as expected. But now let's take a look at square. So square is also doing s.height and s.width. Well, that seems like that should work. We shouldn't have a problem there. Now, one thing I see is we're duplicating some logic. So, this is already a smell that we could probably do some refactoring. We go down a little bit further and we look at rectangle, and we have an int for height, an int for width. And then if we look at square, which inherits from rectangle, we have height and width. But look what happens when we set our width. We are setting both height and width to the same value because a square, by definition, has equal sides. So now this square has broken the invariant that our client expects. Our client expects that a rectangle and a square should be the same thing, but because a square defines itself as having equal sides, it breaks that invariant. So part of this problem goes down to a fundamental issue with the way we oftentimes approach object-oriented programming. It's very natural for us to try to model our code exactly to the real world. And intuitively, that may seem like the best thing to do. But what we find is oftentimes we create a lot of problems for ourselves by trying to force our code to do things the exact same way the real world does. Take our employee example. When we think of an employee has all of these various first name, last name, all of those seem natural to us, but then we're jumping through hoops because the code honestly couldn't care what an employee is. The code only knows ones and zeros. It doesn't, all of these concepts are abstractions that we've created. So now let's take a look at one way that we could fix this, and the way that a lot of us probably would. So we will take a look. So we didn't change anything here. Just to make sure, we're going to run our test real quick and show that this test still passes, and it does. So our area of 6 for a 2 by 3 rectangle passes. Let's try our area of 9 for a 3 by 3 square. and it also passes. But then we've made some changes to how we do our test for our area of 20 for a 4x5 square, and I'm sorry, a 4x5 rectangle, and a 9 for a 3x3 square. If we run our tests, we should see that it passes, and it does. So great, job done. Let's go home. But let's take a look at how we fix that. So what we decided to do in this case, and this is what a lot of us would do, and I've written plenty of code like this, is we're doing this type check. So we're saying if it's a type of rectangle, then do this. If it's a type of square, then do this. So right off the bat, we see that we are now, we're having to open up this code anytime we want to change or add new shapes. So the more complex our system gets, the more we are going to have to be making modifications here. We are creating a scenario where this code is very quickly going to become very rigid, very fragile, and very immobile. So what we could do is use a concept called tell, don't ask. So what we want to do is tell the object what it is we want rather than asking it. So let's take a look at our code that we changed. So we'll notice that here we have now created a new I-shape interface. So before, let me go back to this. So before we had, we're doing these type checks. I keep closing the wrong one. We're now saying that we on our shape interface, we have an add method, and we're going to ask the shape, or we're going to tell the shape that we want its area. So if we look down, we can see that on this interface we've added area as an int that we can retrieve. And so on our rectangle we have it as height times width, and on our square we have side length times side length. So now our square is properly denotes what it is, and when we want to know about it, we don't have to do any more casts. So the benefit we have here is we could add any number of shapes that we want. We could add circles, ellipses, triangles, whatever we want, and this code no longer needs to know. All it needs to say is if I ask you for an area, you can give it back to me. So we've made this code both more sustainable and less fragile. And so we can see that even though square originally inherited from rectangle, we have changed it to inherit from shape, and thereby we are not trying to force a real-world relationship on our object. So before, while in geometry a square may be a type of rectangle, we're not going to be that specific and force that on our code. We're going to take a step back and say a square is a shape, a rectangle is a shape, and we're not going to try to enforce any types of constraints on that could then be violated. So by doing that, we're now able to substitute either of these implementations and not break any of the invariants from our calling application. So that's great. We know how to deal with squares and rectangles. Let's do something that's a little bit more real world. So I have another editor. And so in this case, we're going to have a pretend payment processing system. So many of us have probably done something with e-commerce over the years. That's where I started my career at EBSCO, was in our subsidiaries division doing e-commerce websites. So this is very familiar to me. So in this case, we want to allow a customer to choose multiple payment types and for us to be able to handle them correctly. So let's just take a look at a couple of the things that we have. So we have an enumeration, and right now we support two types of payments, PayPal and WorldPay. And we also have, for simplicity's sake, I have created my own fake implementations of these services, so we're not actually calling PayPal or WorldPay. And so to do that, we've created this refund method, or sorry, this refund string that brings us, that gives us a return. So why we do it as a string? Well, you know, we were kind of lazy, and each payment provider returns different things, and we don't really want to be bothered. We'll let the calling application figure it out. So PayPal will return us one thing, and WorldPay will return us a different. So let's take a look at our code. So we have created this refund service to handle our refunds. So it accepts a service type, an amount, and a transaction ID. And we then call our payment factory to get the payment service. So let's take a look at our payment factory. So in this case, we basically take the service type and we return a concrete implementation based on which type you gave us. If we go back over to our refund service, we can see that we are now doing a check. Again, this is a code smell. Now our refund service is having to know about every payment type that we support. So over time, the tentacles for all these dependencies are making their way through our system. And those tentacles are going to make our system more rigid and also more fragile. So right off the bat, we know we've got a problem. So another thing we'll see is each of these might take different parameters. So in this case, we have a product ID. The other ones only have credentials. I've just put credentials here just for simplicity. This would be another code smell that your developers don't know what they're doing if they're hard coding credentials. So if we look down here, we then call our payments refund method. And then now we are doing some string checking to figure out whether or not we had a success. And if we did, we return true. So if we were to substitute PayPal for World Payment, the only way we can do that is to add all of this additional code. So now we're having to tell our code how to handle each and every scenario that could pop up. And soon, exponential math will tell us that this is just going to become unmaintainable. The more, you know, if we get 20 different payment types, and now we're doing 20 different types of checks, and heaven forbid, WorldPay returns auth and Clear Commerce turns auth, and auth means that it failed authorization. Now you're having to check multiple things, and all of a sudden you've got developers just constantly writing little patches here and there, and you're just making the thing more complicated and harder to understand. So let's look at a refactor. So I'm going to swap branches real quick. So let's take a look at our refund service now. So we still have our payment factory. So we call get payment service, and let's take a look at our payment factory. We've made a couple of changes. So now our payment factory passes in the variables that it needs in order to fulfill the contract. So rather than us having to do that in our refund service, we're basically letting the payment factory do it for us. And even then, we could still, you know, do continuous refactors. We're not done yet, not by a long shot. If we look at our payment system, nothing really has changed. We're still doing things basically exactly the same. So if we go back to our refund, what we'll see is we've eliminated one of our dependencies. We now no longer need to account for every single payment type and do a ISA check, but we're still left with this down here where we're checking strings. And so we're not animals. We don't do string interpretation. We're going to change this to a Boolean. So we're going to refactor again. Okay. I think this is where OmniSharp got out of sync. So let's take a look at PayPal. So we'll notice we've changed our string to a Boolean, and we're asking the PayPal payment class, were you able to successfully refund? So rather than it telling us whether or not it was able to refund, we're asking it. So the benefit we get here is anything specific to this implementation, we keep in this one class. So what that means is now our invariant in our calling application can be that we're going to return a true or a false. We're not going to be expecting a string and having to interpret that. So now we can substitute WorldPay for PayPal or any other payment service that may implement our iPayment base, and we can use that freely. So all of a sudden, we can look at our refund service again, and it's gotten much simpler. So very similar to how Stephen was showing, as we did this refactor, our calling code has gotten much smaller. So now we're down to 2 lines of code. And we could continue refactoring. Now, at some point, like we've talked about before, it may not make sense to continue doing that, but what we're doing is we're making it to where our calling application has as few dependencies and as few violations of invariance as possible. So again, like what Samir was talking about, this is going to allow our code to be modified very easily. We all have run into projects where the longer a project goes, the harder it is to change. That is really the core of Liskov substitution. It's a mechanism for making sure that your code never gets into a state to where you're constantly having to increase the number of places you make a change every time you want to make a single change. So one of the things we probably noticed here is we saw a couple of code smells. So let's take a look. So our code, our non-substitutable code, breaks polymorphism. So when we're trying to allow those changes, the Liskov substitution violations has made our code very, very rigid and unable to be changed. Our client code expects child classes to work in place of their base classes. So when you have a violation, that requirement is broken, and so now you're requiring your child applications to be changed every single time you make a change. So, and what happens is, the more painful you make changing your applications, the less likely you're going to do it. You'll save things up, and you'll do these big deployments because you don't want to do them all the time. And so what you try to do is you try to reduce risk by building these huge deployments when in fact you're increasing your risk. So you're making it far more likely that you're going to break something while trying to do this. So Liskov substitution gives us a mechanism to constantly be checking ourselves along the way to see, are we creating a system that's going to become unsustainable? Again, I am trying to help future me out because he really hates it when I make things hard for him. And so this is really a help. Fixing substitutability, say that 3 times fast, by adding an if-then or switch statement quickly becomes a maintenance nightmare and violates open and close principle. So like I mentioned when I did our intro, generally, if you're violating one principle, you're almost certainly violating a second one. So nearly every Liskov substitution violation is also an open-close principle violation. If you see an open and close principle violation, you almost certainly have a Liskov substitution violation. So sometimes you can actually use that. If you're still not fully grokking the Liskov substitution, you can oftentimes use open and close to tell you whether or not you have it. It's kind of like how NASA looks at the brightening and dimming of a star to tell if there's planets. They may not be able to see the planet, but they can detect the light changes. A lot of times, open and close can detect whether or not we have Liskov. So some of those smells that you'll probably see a lot are tried and true friend, the employee class. We're going to pick on him today. we can see that we're doing an is check. Almost every time you're doing a check where you're seeing is a object, a type of another object, you are probably violating Liskov substitution. That's not to say that there aren't good reasons to do this type of check. It's in the language. There are reasons to do it, but just like go to was in the language, it had a very specific need that pretty much everyone abused. We basically just completely abuse it today. So if you go back to your workplace tomorrow and you start looking through your code and you start seeing a bunch of type checks, you are almost certainly looking at Liskov substitution violations. Another one is if you find that you are not using pieces of the base class. So in this case, we have an abstract class where we have two methods, method 1, method 2. In method 1, we're throwing a not implemented exception, and in method 2, we're actually doing something. So again, this may seem pretty, you might think, well, what's the problem? Who cares? If I'm not using it, throw a not implemented exception, no biggie. Well, by inheriting from this abstract class, we are making a handshake deal with our client that other objects inheriting from this class are going to be substitutable. But when we say that we're just going to ignore some methods, we are breaking that trust. So while for us it may not be that big of a deal, if we have other calling applications that are depending on that, it suddenly becomes very difficult. This also makes it much more difficult other places of our code, because this almost certainly means we're going to have to be doing checks for not implemented exceptions, we're going to have try catches everywhere, or we're going to be doing type checks. So as you can see, a lot of these different violations chain together. One small violation, like not implementing a method that's on your class or your interface, suddenly spirals out of control, and now you're having to account for that all throughout your code. Suddenly, you've made your code very difficult to change and very fragile. This is even more so a problem in a dynamically typed language. So we spent all day talking about C# and static typing. At least we have the benefit that a lot of errors that we can get at compile time. Whereas a dynamic language, you're going to get runtime errors. Now, if someone is not calling this yet, and we have a third party, it can be a runtime error for them as well. So it's something we definitely have to keep an eye on. So let's look at some tips. So like I said earlier, tell, don't ask. So we don't want to interrogate our objects for their internals. We want to tell the objects what we want it to do. So just like earlier, when we said we had the area calculator class, and we were asking the objects, give me your sizes, and I will calculate area. We don't want to do that. We want to tell the object to give us back its area. So now we can centralize anything that will be different for that object in one place. So now when we substitute it, that though all of the assumptions we're making that we're going to get back an area don't change. Another one is consider refactoring to a new base class. So given two classes that share a lot of behavior but are not substitutable, create a third class that both can derive from. So we did something kind of similar with our shape. Before we had square inheriting from rectangle. Again, we were doing our best to try to show a real-world relationship in code, but our code couldn't care less that a square is a rectangle. These are all human concepts, and it has no need for our human concepts. And the robots won't care when they take over either. So what we did is we pulled out that eye shape interface. We used that as a way to normalize across. So now, because it's not inheriting from rectangle, it's inheriting from shape, we can pass that along and we don't violate Liskov substitution. We want to ensure substitutability is retained between each class and its new base. So one thing I would recommend, a good way of doing this is, even though you may never have an instance in your current production code where you are substituting those two, it still is a great idea to write a unit test that does it, because it gives you a very easy, low-cost way to make sure that your code is not inadvertently becoming fragile and rigid. if you're not writing unit tests to prove out things in your code, you're missing out on a huge opportunity. A lot of times we focus a lot with unit tests on what are the things that we can do to ensure that our requirements are met. But we can also use unit tests to ensure that certain expectations are still maintained. So we have the expectation that we should be able to substitute either of these objects. Even though we may not have a requirement to do it right now, by maintaining that unit test, we can ensure that in the future we're able to extend that functionality without running into any problems. So tests like that are ones that you always want to keep in your back pocket, that when you're building new code, that you're building these things in and you're catching these principal violations early when you're writing the software rather than late after you've already deployed it. Because the earlier in the process you can catch a defect, the cheaper that defect is. The sooner in the process you can catch an architectural problem, the cheaper that problem is to fix. So I encourage you, use these things for your advantage. Use unit tests for your advantage. Be looking, asking yourselves, am I finding these smells in my code? Am I doing type checking? Am I throwing non-implemented exceptions? Almost all of these are certainly a Liskov substitution violation. So I want to go ahead and open it up for questions. Like I said, this is one of the most difficult principles, in my opinion, to wrap your head around, because it's something that you really don't think about very much. We all violate it all the time. One of the funny things is we were all working on these projects is we would come into work every day and we're like, yeah, this code we wrote, that violates, single responsibility. That violates Liskov substitution. We're actively researching and doing work, putting these presentations together, and we're talking about code that we wrote days ago that violates a principle. It's hard. This is not an easy thing. So I want to open it up for questions on Liskov substitution.
Have you ever gone back and looked a little deeper? You just talked about a couple days ago you wrote code that's wrong. Have you tried to analyze more than that? Yeah,
so our flagship product, it has, there's one particular method that I think everyone that has worked on that product knows exactly what I'm talking about, and it, I think, probably violates every single solid principle. I mean, I will give us credit. We were very consistent in breaking them all. So that's definitely one that we've flagged, and it's created some official rigidity. So we know that when we have to go and make a change, if we see that we have to make a change in that method, we immediately increase our estimates by 5 points. Because you're going to break something. It was built in such a way that it's not easy to unit test. It has lots of dependencies, and so it's something we've identified as something we're probably going to take a full iteration or sprint to go through and do some refactoring. So this has definitely opened my eyes to a lot of other areas. There's some that were very easy to spot, but even a lot of these principles are very easy to miss, especially Liskov substitution, because most of the time you don't even know what it is. So, and like I said, in a lot of cases you might violate Liskov substitution because you've never had a need to swap those objects. But now going back and looking, you see that, yeah, I've got code that if I ever tried to swap them, I'm in trouble. I know we got more questions on Liskov substitution.
Well, just real quick, you were talking about, the whole going to the shape, rectangle,
Yep.
square issue. And, as you initially started going through it, it was like, okay, we'll possibly just shift the paradigm and make a rectangular type of square.
Mm-hmm.
But again, you're still going to get into that same issue when it comes to the functionality because of the way that you're defining a rectangle as being different from the square. So in those instances, is it just better to rely, on the interfaces at that point, or the interface classes that they can derive from, and just kind of default to that?
I hate to say it should default to it. I would say yes. I think the biggest thing, and honestly a lot of the problems we create, we put on ourselves. So like talking about how we try to model the real world into code. So because in the real world a square is a type of rectangle, we jump through hoops to try to make sure that in code that that's still represented. So I would generally say yes. If you find that you're jumping through these hoops, you're probably trying too hard to model the real world. Same with an employee. You start getting into all those types of things, and that that kind of gets more into real world examples. You might have an employee that is paid hourly versus a manager that might be paid salary, and so yes, they're both employees, and yes, they both get money, but they get paid in a different way. So when you start trying to look at that, it creates a lot of problems.
I think though that maybe the gentleman asking the question might have had a slight misunderstanding about something. Originally, we were trying to replace the rectangle with the square because we said a square is a rectangle. In the later situation, we are not trying to replace the square with a rectangle. We're trying to replace a shape with a square,
Yes.
right? So that's different. If I originally had a square, but it was cast as I shape, and I ask for calculate area, and then I say square calculate area, those two are going to be the same. I was in the second, in the solutions code, where both of my shapes or implemented the I shape, they were not substitutable for each other anymore, right? Originally, we were violating Liskov because we said a square is a rectangle, and so it should be substitutable. In the second scenario, we didn't say that anymore, okay? As a matter of fact, you couldn't even say rectangle equals square, where you previously could say that.
Right.
So you see what I'm saying? So it was in fact perfectly substitutable in the latter scenario. Okay? And you can do the same thing with a manager, right? So we're not saying that all of a sudden all of your objects that implement the interface has to give you the exact same results if you call the same method. Well, then you would need different objects, right? We're just saying that if you start with the base class, you put an object of a class in the base class, or in the interface even better, right? And then you use the specialized one and call the same method. That should give you the same result.
Right, I agree. I guess what I was trying to get to is coming from an object-oriented background. As you said, you're kind of you're pushing the real world onto a program. Instead of looking at it from that object-oriented paradigm, I guess I'm trying to find a way to shift my paradigm out of focus a little bit into that more abstract realm where you are, being able to abstract an idea out into the interface and implement those interfaces instead of trying to inherit purely from base classes.
Well, and the great thing is the very next topic we have coming up is interface segregation, which will definitely help with that. And so we'll see where creating those interface segregations will help break a lot of that, because we, like you said, I was taught, as doing object oriented, all of your sample code is you're trying to model something, in the real world. And so, and then when we developed inheritance, and we basically, went buck wild. We were like, everything's got to inherit. We can't, we don't want to do anything twice. We want to make sure we're doing all these things. The whole point is we are wanting to not break the expectations of the client. So we wanted to substitute without breaking the expectations, not necessarily having to do the same thing. So we could ask for area from two different shapes. They can calculate that differently. Like a triangle is going to calculate differently from a square. But what we're saying is the expectation of the client application is always going to be that it gets back the area for that shape. Which makes it easy to substitute.
So it seems like the smell is that when you see that a client has to know details about its dependency.
Right.
Whereas, asking for area versus having to ask for, side length or whatnot.
And this goes back to the tell, don't ask principle. We're telling the object to give me the area rather than asking the object for its height and width so that we can calculate it. It's one of those things that a lot of times you start doing that because you run into the situation that a rectangle and a square aren't the same, but you've now inherited square from rectangle, so you're like, oh, well, okay, so I'll do a type check and then I'll calculate it differently. So now you're basically working around that problem, and for the longest time, me as a object-oriented programmer, I would work around that problem. I just didn't know it had a name, And now we actually know that it has a name. We have, a formula that you can go memorize and impress all your friends with. Like I said, the way, I think about it now is, we can't substitute a Nicolas Cage for a Tom Hanks. So whenever you think of Liskov substitution, think of Nicolas Cage and Tom Hanks.
One more comment. You opened up by saying you wish you could achieve about half as much as Barbara Liskov, and I wish you good luck with that. But being a woman receiving a computer science PhD is going to be pretty tricky.
Oh, yeah.
Pick some of the other ones.
Yeah. Okay. Any other questions?
What if we like Nicolas Cage better than Tom Hanks?
Well,
Look,
Yeah,
everybody who likes Nicolas Cage better go on the right side of the room.
yeah, there you go. Yeah, I think you got much larger problems than a Liskov substitution violation if you. Well, okay. If anyone thinks of any questions, we'll open up the time once we finish for more. So please do not hesitate to ask, and I'll also be around all day today. So don't hesitate to stop and ask me a question.